Okay, so let's continue with the third lecture by David.
Okay. All right. So we now have the tools we need to tackle an interesting problem. So I'm going to talk again about the spin-2 gap problem, which is one of the things that I discussed at the beginning of the first lecture. So again, the question is about finding an extremal functional that proves that the upper bound on the lowest dimension spin-2 operator is the mean field theory value, 2 delta phi plus 2. Okay, so we know the extremal functional that we're looking for.
Can I ask a philosophical question?
Yeah.
So we seem to be staring at the following problem. So we have this sequence of Bootstrap problems which are converging to some answer, and the Bootstrap problems, I have in mind, are the finite derivative problems.
Yeah.
And for which the functionals have a space which is huge on which they're defined. And then we are hoping to find this extremal functional. And the extremal functional that you exhibited, it seems to be defined on a much smaller space of functions. And so, well, so it's maximally beautiful, but on the other hand, it also has some problems with it. So is your technology, would the technology be able to find a functional which would perhaps not be exactly extremal, but which would have a wider space on which it would be defined?
Okay, so I think that the fact that the functional is defined on a smaller space of functions is intimately connected to the double zeros. One is trying to get double zeros on all the double twist operators, and that comes from this sine squared factor, which is ultimately a difference of phases. Those phases have to come from analytically continuing around branch cuts by a certain amount. So it sort of tells you that in order to get these sine squared factors, you have to write a functional that probes the correlator in these regions where you've analytically continued. And you have to go right to, so if you have a branch cut, you need to take W and W bar to wrap all the way around the branch cut to get the right sine squared factor. I suspect that any functional with the pattern of double zeros on the mean field theory spectrum has to probe the same region of cross ratio space that one probes in these integrals. I suspect that's the case, and then you have to study the boundary of that region and control it, and that leads to these restrictions on the space of functions that it applies to.
But for example, Daly-Mills functionals, okay, it was in one dimension. They also had double zeros.
Yes.
But they were defined on a reasonably large space of functions, so for them there was no problem.
Well, I don't know how to compare the space of functions in one dimension and higher dimension. I need to know which one is larger.
Sorry.
Meaning that it was possible to show for his functions that they were swappable and there was no need to involve.
Sorry, I think it's even clear that the space of this function is smaller than the
It's
space of the
absolutely
derivative
clear.
function.
It's absolutely clear. Derivative functionals are just defined on functions which has a finite number of derivatives.
No, but
Well, your functions are defined on functions which have to have some analyticity
no, but
properties.
this B2 is this B2 cancels some of this double zero, and then it's part of a sequence of functional where we cancel more and more of these zeros. I think when you include the whole tower of these B's, it's not clear to me that it's a smaller space of functional at all.
No, that's not. You're talking about the space of functionals. It's always talking about the space of functions.
Yeah, space of functions.
Yeah, so we fix a functional and ask the space of functions that it acts on.
Can you comment where on your contour is the double light, like the second sheet light limit?
Okay, yeah, so this is W and W bar, and the light cone limit on the second sheet is, I think, let me see, maybe you take them both above the cut, you fix one of them and send the other to infinity.
So you just don't know, like, from the S&T point of view, it's perfectly fine. You just don't know how they behave. Like you don't cross any cuts from S&T point of view. You just don't know what is the simplistic behavior in that.
Yeah, that's right.
What is it in perturbation theory?
In perturbation theory, yeah, that's a good question. In perturbation theory, I think it's clear that it's controlled by the U channel of the. The idea is that in perturbation theory, when you have a light point limit, it doesn't matter what sheet it's on. It's still controlled by particles with high energy blasting between the 2 points. And the leading behavior of that particle is just the classical propagator of the particle. And so I think it's probably very generally true in perturbation theory that the U channel OPE controls the light cone limit on any sheet. Yes.
The location of the double zeros being the mean field theory ones, the double twist ones is sort of naturally comes from the DDs, but would it be better to have something which has other, you could place zeros somewhere else? Like
Okay, yes, I totally agree with that. So I'm going to talk about the extremal functional for the spin 2 gap problem, which has double zeros on the mean field theory values. But what about the spin 0 gap problem? That has double zeros that are not at the mean field theory values. At large spin, they're close to the mean field theory values, and it's a very interesting question how we can construct such functionals. And I don't know.
And
but
it's not just like using instead of some you multiply by w to some integer. If you multiply by w to something that has another cut there, would you
Yeah.
shift those poles?
So you can, if you did that, at least naively, if you just multiply by w to a power, you would shift all the poles for the whole double twist family, which is not what we want. We want something more sophisticated, but absolutely, I think that kind of thinking is very interesting, and it's a challenge for the audience to try to think about alternative constructions. How could you build in anomalous dimensions that depend on spin? That's a great question. Yeah.
Just to clarify, it's arbitrary why you're saying spin 0 is special and higher spins are different. That's just because you're putting different assumptions on spin 0 versus higher spins. Like, of course, for any real physical problem, you would never find all the poles that generalize free field theory for anything. Like, for any physical interacting theory, which is saturating bounds, you would have non-trivial poles for everything.
Yeah, that's right. But the philosophy here is we're going to start by looking at bootstrap bounds that are saturated by very boring theories, mean field theories.
No, I understand what I'm saying, but like, the fact that spin 0 was different, it was just arbitrary. Like, it could have been spin 30 would have been the different one, and every other one would have been the same. If you had chosen to put assumptions on the spin 30 sector and bootstrap that.
Well, no, but I mean, no. I mean, the plots are what they are. You can plot the spin 0 bound, you can plot the higher spin bounds. The higher spin bounds happen to be given by saturated by mean field theory, and the spin 0 one is not.
Wait, but couldn't the spin 0 have been as well, depending on your assumptions?
No, it's just not. I mean, I defined the problem. The problem is to bound the lowest dimension operator in the spin L sector. And now that I've defined the problem, you go and solve it on the computer, and you get what you get.
I mean, but is that for any D? I mean, there wouldn't be some D where general cyclical theory would just be above the interesting case. So kind of, let's say you do D equals 5, and like.
So okay, that's an interesting question. I haven't done this exercise for all D, so I don't know the answer for all D. But
because I think it's basically you're just asking like, is like their interacting IC model which is like above general cyclical theory. So like that happens to be the case maybe in 3D, but like I guess in other cases that would be not the case. And then you just would get general cyclical theory. So I'm pretty sure D equals 5, you just get boring stuff as well.
for spin 0.
Yeah, I think so, because, I mean, first of all, there's no interacting IC model, and even those, like, weird 5DON models would be below the general cyclical theory.
It would be a nice result if there was true.
Yeah, I don't think
it's
it's true. Yeah, I mean, I think the scalar bounds are not mean field theory like in higher than 3 dimensions. At least the ones I've stared at.
Are you saying even when there isn't any?
Even when there isn't a kink, it's not the same as mean field theory.
Okay.
Yeah. Okay. Okay, very good. So, alright, I wrote the word external function up there. I need to figure out what sentence this part is. Okay, so good. The external functional for the spin 2 problem has n star equals 0. And we now have a family of dispersive functionals with n star equals 0, these B2B functionals. And so it's natural to ask, can we construct a linear combination of them that is a candidate extremal functional for the spin 2 gap problem? And so we want to construct some phi 2, which is a linear combination of B2Vs, satisfying the additional conditions that not only does it have n star equals 0, but now we need to say something about how phi behaves on the first double twist family. So we want this to vanish, okay? So it has at least a single zero in everything. And then acting on derivatives of the block, it has to be 0 except when L is 2. Okay, so these have to be true for all even L. These are the conditions that we would like to achieve. And it turns out that these conditions are just enough to uniquely pick out a linear combination of B2Bs that does the trick. However, so that will give us a candidate extremal functional for the spin 2 gap problem. And then we need to check whether that candidate functional is positive. And as I mentioned in the first lecture, that check, at least currently, we have to do numerically. We plot the functional and see whether it's positive. And there are two interesting things. I'll just give you the punchline of the analysis before diving into it. There are two interesting things that come out. One is that this phi 2, that is a linear combination of B2Bs, is positive, but only for a certain range of delta phi. Outside that range, it's not positive. And you might go, okay, what happens outside that range of delta phi? Well, the other important point is that this phi 2, if you decide that it's a linear combination of B2Bs, then it is uniquely fixed by these conditions. But if you don't impose this, then it turns out you can write other dispersive functionals that have the right pattern of single and double zeros. So there's an ambiguity in phi 2. The ambiguity is orthogonal to the space of B2Bs, so we won't encounter it when we do this, but it exists, and I'll try to write down what the ambiguity is. And presumably, if you go into this other region of delta phi, you need to use this ambiguity to fix positivity. Okay? So I'll try to be more precise about all of those later, but that's just a preview of what's going to happen. Yes?
And this phi 2 on the S channel identity must be P1 so that you get
Oh,
or 0. It depends a bit on.
we want it to get 0. We want it to be 0 in the identity. Yeah, that's right.
But that 1, how does it come about?
Yeah, great. Yeah, sorry, you're right. It should give 1. That's exactly right. So what's going to happen is that this 1, which really comes from the U channel identity, is going to cancel against the S channel identity.
It'll be a linear combination of 1s.
Yeah.
Phi 2 is a linear combination of B2.
Yes. Yeah, that's a very good point. Thanks for pointing that out. All right. So,
And so
yeah.
these other, you mentioned this ambiguity is some other set of functions?
Yeah, it's some other set that I haven't written down for you.
Okay, but do you have to relax some conditions? Like what do these functionals not satisfy the B2B to accept?
Yeah, they're not in the space spanned by B2B. I'll talk about them.
Okay.
I'll talk about them. Okay. So, but I guess that's an important point, that we've constructed this B2B, which is a family. It's an infinite family. It depends on V, but it's not everything. Okay. So we're going to try to solve these conditions, and we'll solve them one at a time. So we're supposed to start with this condition, which is that the functional has to vanish on double twist operators of even spin. So actually, it's easy to write down a formula for the action of B2V on the block, not its derivative, but just the block itself. So I claim that this is just equal to the value of the S-channel block at u equals 0 and v. So why is that? Well, it has to do with a calculation that we did a while ago. So remember that the double disk, or the discontinuity applied to the OPE gives a delta function localized on the light cone at the double twist location. Right? That had to do with this this thing that I wrote here, this identity involving theta of x to the lambda, has a pole that looks like lambda plus 1 delta of x. Okay? So, right. So when we go to this first double twist family, then basically what happens is that the x12 to the powers in the OPE turns into a delta of x12. So it turns into something that localizes you on the light cone in the S channel. Okay? So, but we have a double discontinuity, so you get localized on both light cones. So you get a delta of x12 and a delta of x34. So what that means physically is that we have this null integral, so here's our Penrose diagram. We have these two null integrals, and we have the spectator points, and we freeze the null integrals such that they're light-like from the spectator points. Okay? And when we do that, that's just evaluating at u equals 0, and some at some value of v. V is 4 over z13. Okay? So it's just evaluation at that location. And that leads to this formula. Okay? All right, and this is just the conformal block on the light cone, so it can be written in terms of an SL2 block, K delta phi plus L of 1 minus k. Okay. Good. So now there's a cool trick, which is just there's a symmetry property of this SL2 block under v goes to 1 over v. We can use that symmetry property to set this to 0. Okay? So the idea is that we consider the combination v tilde to v, which is v to the delta phi over 2, v to v, minus v to the minus delta phi over 2, v to 1 over v. And by the symmetry property of this SL2 block, it just cancels in this combination if L is even. And that gives us this first condition. There's another thing that cancels in this combination, which it has to do with Balt's question, which is the contribution to the identity operator here. It cancels against the 1 when you take this linear combination. So I'll leave that as an important exercise. Right? Any questions about that statement? Should I say it again?
Yeah, please.
Okay, very good. So we're going to apply this linear combination to the 4-point function. When we do, we have a 1 for each sum row, and this becomes v to the delta phi minus v to the minus delta phi over 2. We also have a contribution from the unit operator in the sum, and we can split that out and evaluate that, and that turns out to give the exact same thing, v to the delta phi over 2 minus v to the minus delta phi over 2. So the unit operator on this side cancels with the S channel identity cancels with the U channel identity in this combination. Okay, so what this does is it cancels.
So in an equation, it's b tilde 2v acting on g00 equal 1.
Yeah, that's right. So the idea is that b tilde 2v acting on g00. This is something that you have to check as an exercise. This is v delta phi over 2 minus v to the minus delta phi over 2. That's the claim. And that's exactly the same thing that you get from the 1 on the right hand side. So they cancel.
I mean, it has to, right? Because the identity operator is the only operator in the mean field theory solution that contributes to the sum of half to go for the b tilde to b.
Yes, yeah, that's right. That's a good point. So that observation follows from the fact that mean field theories would satisfy the sum. Yeah, thank you. Okay. So good. So now we have so now the claim is that 0 is equal to sum, where the sum excludes the unit operator. So that's what the prime means. P delta j, b tilde 2v of g delta j. Okay. Good. So the second condition is harder, and it's easiest to solve, at least as far as I know, it's easiest to solve in Mellin space. So what we're going to do is we're going to start with an ansatz for phi L as a linear combination of b hats, which remember are just the Mellon transform of b. So it's a contour integral parallel to the imaginary axis, b gamma over 2 pi I.
And is the spin out part, or you mean to, or?
Yeah, I'm going to set L equal to 2. I'm mostly going to set L equal to 2. That's right. Okay, so we're going to start with an ansatz like this. And the condition that we get this combination tells us that this function FL has to be antisymmetric under gamma goes to 2 phi minus gamma. So this has to be minus FL of 2 delta phi minus gamma. And this ensures that this integral is really a linear combination of these things. Okay? So that's just an antisymmetry property. But then what comes out of this is some kind of orthogonality property that we want to solve. So let me define the action of b hat on the first double twist blocks. So b2 gamma acting on 2 delta phi plus L, comma L. I'll define this to be a sub L of gamma. And the same thing with the derivatives of the blocks. I'll define it as b sub L of gamma. And then what we have is, so this second condition here, I'll just rewrite it in terms of our ansatz.
Sorry, I think I missed the basic one.
Yeah.
The derivative that you just erased was derivative with respect to delta.
Yes. This is like the coefficient of the single zero. I'll write this.
And B2 was a linear operator that didn't depend on delta. I cannot just act with the derivative inside.
Yeah, it doesn't depend on delta. The delta dependence. So you can bring. Yeah. So what I mean here. So what you can do is you can evaluate this on a general block, G delta J, and then you can take the derivative with respect to delta. And then you can take the derivative inside if you want. But here, what I mean by this notation is the derivative at the double twist location. So a different way of writing this is b2 gamma hat of G delta L, derivative with respect to delta, evaluated at delta is 2 delta phi plus L. That's a equivalent formula.
That's because the blocks for in your conventions depend on delta and delta phi. That's why I cannot just take derivative with respect to delta phi of the first equation.
Oh yeah, that's true. Yeah. That's right.
Sorry, on the second line over here, is it f sub gamma of gamma or f sub L of gamma?
This is, sorry, f sub L. Yeah, I got confused myself about the upside down gamma. Thank you. Okay. All right. So, So these are some definitions, but we can actually evaluate this. So I wrote a formula for the action of B2 hat using Mellon space. And so what it means is that these A gammas are essentially Mach polynomials. So they're related to these Q's. In particular, they satisfy an orthogonality equation. The A's do by themselves. Let me just write it down. So there's an orthogonality equation that is basically orthogonality of Mach polynomials which is orthogonality with respect to this measure with these gamma functions. And the idea is that AL of gamma, AL prime of gamma is some normalization constant times the Kronecker delta L prime. Okay. Now, right. So that's one fact that follows from the explicit formula for the action of the functional in Mellon space. And here's another fact. These are facts. Another fact is that the B gammas are related to the A gammas in this way. That mistake. Okay, so for even L, there's an identity relating the BLs to the ALs. Okay, so, right. Now the condition that we want to solve is, so what we want is that delta L prime is equal to the integral d gamma over 2 pi I of f sub L, the function that we're trying to find, times BL prime. Okay, this is just a different rewriting of the condition for where the single zeros are on the leading double twist family in terms of our ansatz. And now, this has to be true for L even. So we can plug in this formula and use the antisymmetry property of F to rewrite this in a different way. This is just the integral d gamma f sub L of gamma d A sub L prime of gamma d gamma. So from here, the solution to this condition is almost immediate. So I'll just write the solution and then you can check for yourself that it's correct. So the idea is that it's just the integral of A gamma. Okay, so I claim that this is the solution. Why is it the solution? Well, the idea is to take this formula and plug it in here, integrate by parts. So you throw the dd gamma from here onto the FL of gamma. By construction, that produces the integrand, and this integrand gives us exactly what appears in the orthogonality condition for the A sub S. Okay? So then you just have to worry about this, and this has to do with just checking a boundary value for F sub L. Okay, so we found a unique solution to our conditions. And so there's a unique linear combination of B2Vs with the appropriate pattern of single and double zeros. And so then we should, and so we now have a candidate extremal functional for the spin L gap problem. And we can set L equal to 2 and check whether it's positive. Check whether it's positive. And so here's what you find. So you find that phi 2 is positive for scalar blocks above the unitarity bound. You find that it is.
Sorry.
Yeah.
Again, that first equation just follows from the first one up there, right?
This equation
This
is a
is the-
choice. This is the solution to this condition. So we're trying to solve for F sub L, and the claim is that this is the solution.
I thought F sub L was defined.
So F sub L was, this F sub L is what goes into our ansatz. So if we can fix F sub L, then we will we'll know phi sub L.
Is it obvious that it satisfies the antisymmetry property from the definition?
Yeah, it should be obvious. So the Mach polynomials satisfy an antisymmetry property, and that should be what you need to prove the antisymmetry property of this. Yeah, that's a great question.
Where did this last equation on bullet come from?
So this equation was a rewriting of the statement that phi L of the derivative with respect to delta of g 2 delta phi plus L prime prime
Got it. Is equal to delta output.
is equal to delta L. Yeah.
So the anti-symmetry comes from the integration, extremes of integration, right? Because the Mach polynomial is being integrated over.
Yeah, you need this and this, probably. You need that you're integrating over your contour has a symmetry property and the integrand has a symmetry property. Okay, alright, so on scalar blocks this is indeed positive. On spin 2 blocks, it has the property that one wants. It's positive for delta bigger than 2 delta phi plus 2. But then there's the subtlety that I mentioned. On higher spin blocks, it's positive for even j, and delta bigger than some tau naught that depends on d and delta phi plus j. Okay? And tau.
Sorry, now that you found it, is it simple in position space?
Good question. So yeah, it doesn't seem to be that simple in position space. But I mean, yeah, I don't know. We weren't able to. Let's see. So for special values of delta phi, you can write this as an integral of b to v times a function of v. I don't think we were able to actually do that integral over v. But for other values of delta phi, we couldn't even get that far. It's a little hard to unknown transform this. But I'm not sure. It might be possible.
What about in Mellon space? Is there some natural ansatz to start with to derive directly this function like as a dispersion relation?
I'm not sure.
Sorry, what is tau naught?
Yeah. Okay. Good. So now I'll explain what tau naught is. So tau naught is some function that depends on d and delta phi, it's increasing, and the question is when it's above or below the unitarity bound. So when tau naught is below the unitarity bound, then great, we've achieved what we want. When tau naught is above the unitarity bound, then we have a problem because our extremal functional is negative in a place where we wanted it to be positive. So, so the question is, for what delta phi does tau naught cross the unitary bound? And the answer depends on d. So when d equals 3, it's something between 1 and 2. And when d equals 4, it's something between 2 and 3. Okay? So what this means is that below these values of delta phi, we have a solution to the spin 2 gap problem. But above them, we don't.
This is some number determined numerically. It's some number.
Yeah, it's determined numerically. Yeah, that's right.
So just checking, that B hat in the last lecture was the Mellon transform of B, but in this setting, should we think of it as a Mellon transform of the modified B, which killed the identity?
Yeah, you can think of it as a Mellon transform of the modified B if you like. That's encoded in the fact that F satisfies this antisymmetry property.
Oh, that was...
Yeah, so we have this still the transform of B. With the transform, you should have phi L as a transform of B tildes.
Okay, yeah, F is what it counts with.
Yes.
What's the status of this positivity? It's just really plotting, or
Yeah, it's just plotting. Yeah, it's plotting. So yeah, maybe I should say how that plot is made. So it's a question of how you evaluate this functional. You can evaluate the functional by starting from the Mellon space formula. And the way you can do it is, I think that what happens is you can do the integral over gamma prime analytically, and then you have to additionally integrate over gamma. Right? So f sub L of gamma is defined by a gamma prime integral, but then we have to integrate over gamma as well. That we have to do numerically. And then you also have this sum over m. And there we truncate and approximate it by finding the row terms. I should say that the numerics are not easy. Like it's not, there isn't like a fast way to evaluate this very precisely. And that would be very nice. I think it's just for general applications of dispersive functionals, it will be important to be able to evaluate them efficiently and precisely. And I think that's an open research problem.
So it looks like positivity comes as a surprise, like we have no a priori expectation.
Yeah, that's right. Positivity comes as a surprise, and it in fact only holds for certain delta phi's, and above this crossing value, it doesn't hold. But above this value, we still think that the extremal functional is saturated by mean field theory. So what gives?
Can you say something more about this critical value? More precisely where it is?
No, I can't.
You don't know.
Yeah, I don't know.
Sorry, can you repeat? Tau naught is an increasing function of delta phi? Or?
Yeah, it's an increasing function. Just experimentally.
But did we really do the plot that far to be sure that in that range mean field theory is still a solution? Because when we discovered this mean field theory, we were really exploring a very small range of delta phi's.
Yeah, that's an interesting question. So Slava's question is about what happens if you do the numerical bootstrap at larger delta phi. And I guess I'm not sure. Not sure what happens.
I think it's a boundary will diverge at some point.
It will diverge at some point? But how does that depend on the derivative order?
Say 7.
Yeah, the question is what happens is the derivative order goes to infinity. Yeah, you're absolutely right. That's true. That does tend to happen if the boundary diverges at some point.
Oh, this might be even physical.
Maybe. But well, let me talk about the next thing, which is ambiguities in this. So the idea is that there's an ambiguity in phi 2, where what we can add to it what you might call so when you can add to it a functional that has to have the following properties. So first of all, it has to have Reggie spin bigger than 1 in order to be a valid functional. And for dispersive functionals, this means Reggie spin 2. So k equals 2. And it also has to vanish on all even L double twist blocks. Okay, so these such functionals are perhaps confusingly sometimes called odd spin functionals, because their supports are on odd spin. Their support is on odd spin double traces. They vanish on all even spin double traces, so their support is on odd spin double traces. And here, this spin is not a Reggie spin. So there are two different notions of spin, and this is not k. Okay? K is 2, which is not odd. So okay, so we can add here. I would say our understanding of the space of these things is not systematic, but you can construct them by hand. And so what you can do is you can look at contour integrals of the form that we have with some kernel. And you can just cook up kernels that have this property. And one of the key ingredients in these kernels is that you have to allow yourself to have poles at w equals w bar. So you're allowed to write meromorphic functions with poles like this. And it's not obvious, but these don't actually spoil the dispersiveness properties of the functional. And this was an observation made in Leonardo and Dallimil and Shinon's paper on analytic functionals, that these kinds of things are admissible. So you can just cook them up, and you can take linear combinations of their functionals that have all of these properties. And what we don't have, I would say we don't have a good parameterization. Well, we have a conjectural basis for this space, but we don't have a great parameterization of it in the nice way that we have a parameterization of B2D. So I think this space needs to be understood better, but it does exist. You can cook up examples. The existence of these things means that we're free to add them to our phi2. And in principle, what might happen for a larger delta phi is that you're forced to add these things to fix positivity. And it may or may not be possible to do that. That's something that we haven't explored. So there's this ambiguity, and I've been very vague about it. So what can we actually check? Like, is there something we can check, like about the validity of this phi2? And there's a kind of cool fact that this ambiguity does not affect the action of the functional on scalar blocks. So this is a cool fact. So the claim is that an odd spin functional, let me call it psi. The claim is that an odd spin functional with k equals 2 necessarily vanishes on scalar blocks. What this implies is that phi2 acting on the scalar block is unambiguous. So what you can do, I'll prove this in a moment if you guys want to see the proof. So what you can do then is you can make a plot of phi2 acting on a scalar block. And that is a good prediction that's completely independent of this ambiguity. And you can compare this to the numerical bootstrap. There you get a spectacular agreement. So the numerical bootstrap gives you some function of delta, and a bunch of functions of delta that depend on the derivative order. As you increase the derivative order, you see these functions converging to this crazy analytic function that you can compute from the Mellon space formula. And it's an analytic prediction for the infinite derivative limit of a numerical bootstrap problem, which I think is very interesting. So it tells us that there's something not crazy about phi2.
But what about if you take act on the spin 2, then it does not converge, even if you are in this range?
Excellent question. Yes, that's right. So what if you look at something that is subject to this ambiguity, like spin 2 blocks? So if you do the numerical bootstrap and compute the action for the numerical functional on a spin 2 block, then indeed, it does not appear to be converging to phi2, and in fact, it doesn't even appear to be converging. At least it's much less clear that it's converging. It's jumping around. So I think, what it seems to indicate is that the space of extremal functionals for the spin 2 gap problem is actually a space and not just a unique one. The numerical bootstrap picks out an element of this space that depends on the details of the numerical bootstrap. The element of that space that it picks out, it may not even, I'm not exactly sure what determines which element of that space it picks out, but it may or may not have a limit in this space. This is conceptually interesting. Normally we think of the extremal functional as being unique. I guess there's evidence in this case that the extremal functional is not unique. So you can, in other words,
the zeros are the same.
The zeros are the same. Absolutely, the zeros are the same. But you can have two different solutions that are both positive that differ by this ambiguity. It seems to be the case.
Could you use this ambiguity to get a functional which is defined on a bigger space of functions?
Possibly.
if you pick a, let's see, parametrically, if you pick a region where this tau 0 is bigger than entirely bound, and for these higher spins, you impose your numerical bound there. You impose your numerical gap there. And you look at what you are getting numerically, the functionals. Do they converge to phi 2,
I think,
because you said your tau 0 is above unitary bound at some weird cases. If you impose these gaps, would it help you?
yeah, I'm not sure. I don't know. Yes?
Can you add some new layer in the Bootstrap algorithm, like minimizing multi-collision that makes you converge within this space?
Yes, probably you can add a condition that makes the solution unique. Yeah. Yeah, that would be, so you're trying to minimize, I mean, normally you don't expect you can add another condition, right? When you write down your some indefinite problem, you have a normalization condition, you have an objective, and those are the only things that you have. But the claim is that the solution lies not on like an extremal vector, but on an extremal face of some kind. So you somehow need to put in an additional condition. I think what that means is modifying your objective. So your objective is somehow degenerate along this face, so you need to tilt it so that you're sent to a corner of the face instead of just somewhere on the face.
Here we don't have an objective, right? It's just solving yes or no. It's a gap maximization problem. It's not an e-coefficient maximization problem.
Yeah, you're right. Let's see. I see. So maybe if you phrase it in terms of a limit of OPE optimizations, then maybe that's sufficient.
Sorry, what do you want to add a condition?
Let's say we want to minimize the navigator function, and that's our condition. Maybe that has a unique solution. And then we additionally go to where the 0 of the navigator is. Yeah.
I wanted to come back to Shai's question. Say you wanted to have your extremal functional have zeros in the location of the actual dimensions of the higher spin operators instead of the double twist. What would you do differently?
Yeah, I don't know. I don't know how to construct such a thing, but I think it's important to think about.
But could you, for example, if you just look at B4 and B6, and at least with up to some finite level, you could rearrange the low twist of spectrum, right? Not the arbitrarily high spectrum, but the low twist spectrum you could.
Yeah, that's right. So you can definitely make double zeros that are not at the mean field theory location by just adding together functionals that are not 0 at the mean field theory location. But when you do that, the double zeros have to be created by taking linear combinations. It's not building in the double zeros in the way that we built them in here. I think the question was how
I understand, but perhaps that's already a very good approximation that we keep the high twist stuff fixed, but the low twist stuff we let the numerics choose what's better, and maybe that'll be a more efficient way of approaching the exact solution.
That's right. Good. So you're getting to the question of how useful these might be as a basis for the numerical bootstrap. Yeah, that's good. So that's something I was going to talk about. Maybe I'll talk about that next.
So, go back to 5D for a moment. Why do you expect that the 5D scalar upper bound would not just be generalized speed field theory?
I think the burden of proof is on you, right?
Yeah, I think it's just not. I mean, I guess I haven't made many plots in 5D.
But I mean, I have the proof. It's like we had this paper with Sylvia and Ron from like 8 years ago, where we studied 5D one model for any value of n. And indeed, the reason why it was difficult to do this is because whatever interactive theory you expect is below generalized free field theory. And
Yeah,
so
but I don't think that means that the bound is necessarily a generalized free field theory. So in 4D, the bound is definitely not the mean field theory line. It doesn't have a kink, but it's a nice curve.
Is there any way you could try to reproduce that using these functionals? Because I mean, if it should be something kind of boring, like some generalization, generalized free field theory.
Well, the curve looks boring. It doesn't have any kinks, but we don't know theories that saturate it in 4D. I don't know about 5D, but I think it's probably the same story. Well, actually, yeah, it'd be great to see a plot in 5D. So maybe you can have it for us by
Yeah,
tomorrow.
I can show you. I can show you now or after yours.
Okay.
If
Maybe
you
how
try
about
to do even D, it's okay. They go to 6.
Okay. Good. So
Sorry, I have a question. So
Yeah.
does the ambiguity, can the ambiguity change the function of tau 0?
yeah, that's the whole idea. So this ambiguity has double zeros on all the mean field theory operators. So by adding that, you don't change anything about where the mean field theory operators are, but you do. But it is non-zero away from the mean field theory operators. And this tau 0 is all about the value of the functional between mean field theory operators. So yeah, you could imagine trying to move it around and decrease it.
Sorry, is this tau 0 below or above 2.5?
The question is, tau 0 is the value of, let's see, is it below or above 2 delta 5? So this thing was about when tau 0 crosses the unitary bound.
Yes, but there's
D minus
another higher stuff, right?
I think if you take delta bigger than this, then it will also cross 2 delta 5. Probably. No, wait, sorry, let me think. Does that even make sense? That's possible. That does make sense. That's possible.
So it's cross.
It could cross, but still maintaining a double zero at the mean field theory application. That could still happen. The double zero could just be from below. Okay. Good. So since Joao was asking about it, I was going to talk about the Lightning Bootstrap, but I'll swap the order of things and I'll talk about the numerical bootstrap first. Actually, before I do that, I can ask, does anyone want to see the proof of this? It's kind of cute, but we have limited time, so. Okay, no one's clamoring for it. You can ask me about it after. Okay, so applications to numerics. So the derivative functionals that we use in numerics have three important properties. So one is swappability. Two is some form of completeness. As the number of derivatives goes to infinity. So this lambda here is essentially the number of derivatives. And three is what I'll call asymptotic positivity. And what I mean by this is that it's possible to take finite linear combinations that are positive outside a compact set of delta and j. So I'll say that again. You can find a finite linear combination of derivative functionals that's negative only inside a compact set of delta j and positive outside. And in fact, it's very easy to construct these things. You just look at like the lowest order derivative, does it. And you can just look at the plots from the original Bootstrap paper and see that these things are clearly positive. So it's very easy to satisfy this for derivative functionals. But these are three key properties. If you don't have asymptotic positivity, then you're never going to be able to prove a useful Bootstrap bound. And of course, swappability is necessary for everything to make sense. Now, completeness as lambda goes to infinity is not a necessary property, but we do want it because we want to get the best possible bounds. Good. So what about dispersive functionals? So for dispersive functionals, I've discussed swappability a little bit. The question of swappability is much more delicate than it is for derivative functionals, but you can construct swappable dispersive functionals. The question of completeness, I would say, is sort of an open question. I mean, there's a conjecture for a complete basis of dispersive functionals with spin 0, due to Leonardo and Dalrymple and Chinon. And it's a very convincing conjecture. And you can kind of soup up this conjecture to get a conjecture for a complete basis of functionals with spin 2 or higher by taking linear combinations of their basis elements.
When you say spin, you mean register?
Reggie-spin, thank you. Yeah, Reggie-spin.
And sorry,
What's that?
You mean that they're going to be complete at the given spin. So if you fix spin to be 2, then they're complete. Or
Yes, that's right. So the guess, the hope, the claim is that if you ask for the space of functionals with Reggie spin 2 or higher, then you can write a basis for this space by taking linear combinations of their alphas and betas. Yes?
From a practical perspective, you could just use both the dispersive functions and derivatives, right?
Right. So that's right. You can always do that. So if you really want to worry about completeness, you can just throw in some derivative functionals as well. And that's true. Yes. Good. Okay. So completeness, I would say there are still questions about it, but there are reasonable guesses for good sets of dispersive functionals that may be complete. So asymptotic positivity is trickier. So I think it's the case that if you take any of these basis elements that they had, they're not asymptotically positive. That any finite linear combination of them is not asymptotically positive. Instead, you need infinite linear combinations to get something positive. And an example of such an infinite linear combination that is positive, at least for some range of delta phi, is phi 2. So this is asymptotically positive. At least for some range of delta phi.
For all delta phi?
No. The problem is that for large delta phi, it's negative below some twist gap. So there's a non-compact region. By compact, I mean compact in both delta and j. So it means you can't have j goes to infinity. Yeah. So as far as I know, this is the only example that we have of an asymptotically positive dispersive functional. So,
But anybody has tried very hard, right?
but no one has tried very hard. So if no one else is going to try very hard, then that means you have to throw in phi 2 into your basis. Now you might go, what about Alshandra's observation that you can just throw in some derivative functionals there too? But I don't think that works because the derivative functionals have different asymptotic behavior at large delta. They die exponentially in delta, but but the dispersive functionals do not. So any finite number of derivative functionals will not fix asymptotic positivity. So you need this, or you need to go and construct something else and then use that. Okay. So this is kind of weird. It's a weird situation. Yes.
Your derivative functionals also don't have the double zeros if you wanted to build in. Right? So if you're going to add them to the space, then I think you just lose all the nice properties of these functions.
Okay, yeah, that's a very good point.
Couldn't that be even positive? Because useful because since asymptotically phi 2 dominates, the other ones will just slightly change the probability.
Yeah, that might be what you want. That's right. So maybe I should have said before starting all of this, why would you even be interested in using dispersive functionals in numerics? And that's related to this observation. So right. So one of the things that you see the numerical bootstrap doing is trying very, very hard to reproduce the double twist operators in the spectrum. By which I mean, if you plot the functional in any finite number of derivatives, you get a few double zeros, and then it shoots off to infinity. As you increase the number of derivatives, you get more and more double zeros, and the functional is trying very hard to make this oscillating pattern. And so one nice thing about dispersive functionals is it builds in this set of zeros at the mean field theory locations. And so it looks, at least naively, like a better approximation to what we want the extremal functional to be. So that makes it natural to try to incorporate it, and you might even say that by using dispersive functionals, you're building in the light cone bootstrap, so that you're not requiring the computer to work so hard to rediscover the light cone bootstrap.
There's something I'm confused with. So phi 2 has a bunch of double zeros, right?
Yeah.
So suppose that we use it in a numerical problem for which the answer is not interfering.
Yeah.
So these double zeros will have to be shifted by some amount.
Yes.
But there are some.
So there is no asymptotic positivity because asymptotic positivity means it has to be strictly positive.
Right, they're not, these, the
Or
dispersive
how-
functionals are,
How are we ever going to show that once you add something to phi 2 which is not strictly positive, it has to be not strictly positive, right? Because
yeah, I see what you're saying. Yeah, I see what you're saying. Yeah, if you add anything that decays similarly to phi 2, it's gonna move the double zeros, and that probably means it either means removing all the zeros or making negativity.
well, of course, we might settle for some functionals which always have double zeros above a certain huge
Yes.
delta, and
That's right.
and that would be okay.
Right, and I think the basic idea is that those functionals might be better approximations to what we want than functionals that are growing polynomially at large delta, which is what the derivative functionals do. Well, polynomial times an universal exponential factor.
Okay, that's nice too.
Yeah, that's the idea. So it's a question of whether functionals that have double zeros above some twist and then have some, are some whatever linear combinations you want below that twist, maybe those are better approximations. Maybe that's a better space. Yeah.
I think Miguel and Bernardo in one dimension have some evidence that this is indeed a better space if you're about to converge faster.
That's right. That's a good point. I should have mentioned their work. Yeah. So they explored this problem in one-dimensional CFTs, but it's unexplored in higher dimensions.
These all spin functionals, they are not asymptotic concepts.
It depends how you construct them. So if you make them by taking finite linear combinations of Leonardo, Dalrymple, and Chinon spaces, then no, they're not. But you can do something more general. And then, yeah. But the role of the unspin functionals is adding them to phi 2. So it's not, you don't need this part to be asymptotically positive. You need the sum to be asymptotically positive. So that's a different question. Okay. Good. So I think that this is interesting to explore. There are a couple technical challenges that would come in trying to do this that come to mind. So the first one is efficiently evaluating these functionals. So for example, phi 2, I described how to do it using the Mellon space formula, and that's not efficient, and it's hard to get high precision. So again, I think this is an important open problem, finding good ways to evaluate dispersive functionals, their action under formal blocks. And I think it's necessary to do that for any numerical applications. The other comment is that these dispersive functionals don't have the same positive times polynomial of delta structure that the derivative functionals do. And that means you cannot apply semi-definite programming in the same way. And so one approach that you might take is just going back to the original Bootstrap and discretizing in delta and j. And that approach should work. But it could be technically tricky to get right. And the reason I say that is because this is the approach, just from experience, this is the approach that we use in the EFT Bootstrap. And it is technically tricky to get right. There you discretize in M and J because the functionals are more complicated than positive times polynomial. And yeah, and you have to work very hard to make sure you have good approximations in all regions. Okay. Good. So that's what I wanted to say about numerics. Maybe what I'll do now with my last half hour is I'll just make some comments about the light from Bootstrap.
You did 1 hour already, right?
Yeah, I'm joking.
What's the real estimate?
The real estimate. These are very short comments.
But lunch is not till 1.
You have nothing to do anyway.
The audience enthusiastic.
So let me just mention the like from Bootstrap, and then we'll close this chapter. Actually, you know what? In order to talk about the Lakeman Bootstrap, I have to give the cute proof of this. So let me do that. Okay, so let's go back to that statement. Okay, so the claim is that the claim is that if you have an odd spin functional with k equals 2, then its action on the scalar block vanishes. And the proof is really cute. At least I think it's cute. Let me just so the idea is to take this functional and apply it to the fully crossing symmetric sum of Witten diagrams, Witten exchanges, where you exchange a scalar with dimension delta. Okay, so now this sum of Witten diagrams has some important properties. One, it's crossing symmetric, that is obvious. And the other is that it's Reggie bounded with spin 0, and 0 is less than 2. Okay, this is just a fact about the Reggie growth of Witten diagrams. In general, the Reggie growth is determined by the spin of the thing that's exchanged. So that means that this thing is in the domain of psi, and by crossing symmetry, this is equal to 0. Okay, maybe I should have, yeah, psi is on odd, so an odd spin, so it has support on odd spin mean field theory operators, has k equals 2, and of course it's also crossing antisymmetric. So that when we act on a crossing symmetric thing, we get 0. So this is 0, and now we can evaluate this in terms of the conformal block expansion. Well, this sum of Witten diagrams has an S-channel expansion that involves the S-channel block for the exchanged operator plus double traces with even spin. Okay, but then of course psi vanishes acting on these. So we get that psi acting on G delta 0 is 0. Okay, so that's the proof. And this is the thing that implies that phi 2 is unambiguous when acting on a scalar block. So then you can think about phi 2 acting on this same combination of Witten diagrams. And what you prove is that phi 2 acting on G delta 0 S is minus the action of phi 2 on the double traces that appear here. What does that do? It picks out the anomalous dimension of the spin 2 operator in this double trace sum, because that's what phi 2 does on double traces, right? What is that? Well, now it's a question about Witten diagrams. What is the anomalous dimension of the spin 2 operator in this sum of Witten diagrams?
Of the leading twist.
Of the leading twist spin 2 operator. And that you can compute, if you like, using the Lorentzian inversion formula. So what it means is that we actually get a formula for the action of phi 2 on a scalar block, which looks like this. So it's the OP coefficients of mean field theory for the leading twist spin 2 operator times the anomalous dimension for the leading twist spin 2 operator that would be computed by the Lorentzian inversion formula. Okay, so if you like, you can think about the contribution of an operator in the S channel with dimension delta to an anomalous dimension in the U channel. Or it's the same thing as the contribution of an operator with dimension delta in the T channel to an anomalous dimension in the S channel, which is maybe more familiar convention. So this is actually the function that that the numerical bootstrap matches to. It's kind of cool. Okay, so why am I mentioning this? This is relevant to the light cone bootstrap discussion. So, okay, so these dispersive functionals give, as I mentioned at the beginning of these lectures, an alternative approach to the light cone bootstrap. Actually, I need to write a generalization of this formula that I just wrote. So this equation for phi 2 is a special case of a more general result, or at least a conjectured more general result, of the following form. So phi 2 is what is it? It's a dispersive functional that has a single zero on the mean field theory operator, the leading twist mean field theory operator with spin 2, and it has Reggie spin k equals 2. Okay? So, conjecturally, there exists beta NL improved, which has an analog of these properties. So it has a single zero on the NL mean field theory operator, and it has Reggie spin L. Okay, so this is a confusing situation in which the two notions of spin are locked together. Okay, that hasn't happened in these talks before. We've had two notions of spin. One is the spin of double trace blocks in the S channel, and the other is the Reggie spin. They've been completely different concepts. But now we're going to set them equal. Okay, and so I'm just pointing that out. So conjecturally, this exists. And phi 2 is an example of beta 2 0 improved. So this is beta 2 0 improved, in case you want an explicit example of what I'm talking about. So conjecturally,
beta 0 2?
oh yeah, thank you. Yeah, good. 0 2 improved. Okay. So if such a thing exists, then following this exact same argument and an identical argument, you get a similar formula for its action on any double twist block with spin less than L. And it should give you what the inversion formula gives for gamma. So this is true for L prime less than L. Okay, and if you want to be concrete, you can think about phi 2 as an example. Okay? Good. So
question. So this is the result for the inversion of a single T-channel operator?
Exactly, yeah. It's the inversion of a T-channel block with these quantum numbers, and it's the contribution to a S-channel block with S-channel double trace with these quantum numbers. Okay, good. So I showed you how to construct phi 2. We do not have a general construction of these beta and L imps. That's another interesting open problem. By the way, these are probably not unique. There's the similar kind of ambiguity in these. So the problem is to construct an example for each and
do you expect positivity?
No. So in this definition, I have not imposed anything about positivity for beta and L. And in fact, it's not too hard to construct examples that don't have positivity properties. Phi 2 is interesting because it has additional positivity properties. But yeah, you can decide what problem you want to solve. Yeah.
So the action of the function is like you compute the inversion formula, you pick a particular pole of what you compute, not C delta J.
Exactly. Yeah, you compute you apply the inversion formula and then you pick the coefficient of the double pole.
Could you have constructed the functional by going to that pole of the inversion formula somehow?
Right. Well, yeah, the functional is somehow related to that, but it's not that. So remember, like I said before, you cannot apply the inversion formula and then go to the pole. That's not allowed. You can't do that to the 4-point function and also expand in the T-channel blocks. Like these two things The expansion in T-channel blocks doesn't commute with go into the pole. However, what you would get if you did that is built into the functional. It is built into a nice rigorous functional. And we're going to see the significance of that in a second.
So J and L prime are the same.
What?
J and L prime are the same in your formula.
Yes, thank you. Yep. Thank you. Okay, so let's suppose we have such a thing, and again, concretely, you can just think about phi 2. And let's apply it in a theory that has an operator close to the mean field theory. And let's just look at beta 0L. Yeah. Okay. So we're going to apply this to physical 4-point function. And what do we get? Well, if there's an operator close to this mean field theory operator, then we can isolate its contribution and put it on one side of the sum that we get. That's going to give us the OP coefficient of that operator, and then the action of this thing on the conformal block is going to look like the anomalous dimension of that operator plus order of the square of the anomalous dimension. Why is that? It's because this thing has a single zero at that mean field theory location, right? And the operator O, I'm going to assume, let's assume O is close to this mean field theory operator, phi 0 L. Okay? So if this is true, then this formula just follows from the form of the functional. And meanwhile, this is going to be equal to a sum over everything else. So it's going to be equal to a sum over delta prime and j prime that are not equal to the quantum numbers of this operator O of p delta prime j prime times beta m 0L applied to this block. Okay, that's just putting everything on the other side. And now we're going to use this interesting formula here. And this formula applies when, yeah, maybe I'll call this L prime instead of J prime. Just
Sorry,
to connect.
what is delta J? Is that the dimension from the spin of O on the left, the thing you're applying?
Yes, that's right. These are the quantum numbers of O. Maybe it's, I'll just, or it's right, not O. Okay. Good. So we can now take this sum and we can split it into two pieces. So we get a sum over the operators with L prime less than L. And that gives us, using this formula, it gives us P MFT 0L times the sum over L prime less than L gamma 0L delta prime L prime. And then minus everything else. L prime bigger than L, P delta prime L prime beta m 0L GS delta prime L. Okay, so this is kind of cool. So what are the features of this formula? First of all, on the left hand side we have the anomalous dimension of the operator, which we might be interested in computing. But we also have some small correction term. Okay, so this is what I meant in the beginning lecture when I said anomalous dimension plus small. So this is the small, and it's computable. On the right-hand side, we have exactly what we would have gotten from blindly applying the Lorentzian inversion formula to all the operators with spin less than L.
Don't you also need there the P delta L?
No. So, yes. Yes, maybe we do. Let me think. Yeah, we do. Yeah, thank you. Thank you. Okay? So this is what we would have gotten from blindly applying the Lorentzian inversion formula. So for example, in the Ising model, we among this thing would be included the contribution from epsilon. Let's say we were computing the anomalous dimension of the leading spin 4 operator, so L equals 4. Then here we would have the contribution from epsilon and from T, for example, among other things. But minus some other stuff. This stuff and this stuff are somehow the things that make this that make this actually valid, unlike the trying to take the inversion formula and going right to the pole. So this is a valid sum rule. And now the challenge, depending on your application, is to control these other terms. And so this is one relationship between these analytic functionals and the light cone bootstrap. And I would say I should say I don't think this has not been explored very systematically at all. So this is another interesting thing to think about.
But it's important that these other terms, that this is dispersive functional, so that you want to be able to say that there are small associations, because otherwise I could have just taken the return block expansion, the return block to the left hand side and said, okay, it depends on E and gamma, so.
Yeah, that's right. So yeah. If you want to control these terms, yeah, naively you need to know something about the theory. You need to know that the operators are mostly close to the mean field theory values. Yeah, so for example, if you're in a large N theory, then these are great. These sum rules are great. If you're not, then maybe there are some physical arguments that you can make, or I mean, so if you look at Simmons' paper on the leading first trajectory in the Ising model, he has a discussion of sort of how close to mean field theory the Ising model is. I guess Johan talked about something like these ideas in the talk that I missed most of when I arrived late, but you discussed sort of how close to mean field theory the Ising model is? No.
Not really.
Not really. Okay. So yeah, the hard question is what do you do about this sum? What can you say about it? Good. Okay, so that closes the chapter on applications of dispersive functionals to general CFTs. And what I'll do with the last lecture tomorrow is I'll talk about applications to holographic CFTs.
Any other question? Everybody is desperate for lunch.